Yeah, so thank you for coming, everyone. For my workshop today, it's titled Zero to NLP Hero. So the overall gist of what we talk about today is just kind of NLP techniques from various domains. And for this, I'm going to fully assume you know nothing about machine learning. So it's fully from zero all the way to these really advanced state-of-the-art techniques. And so the big focus here is going to be less about telling you what these things are, but more about actually showing you code so that when it comes to your projects, you can use them in the things that you're doing. So before we dive into all that stuff, first, a little bit about me. My name is Liam. I'm a PhD student here at the University of Waterloo. I'm in my third year. And mainly what I research is natural language processing. I also study graph machine learning, multimodal machine learning, so images and text, and can combine them together, with my main focus being on social media text and tackling hate speech. Before doing all my research, I also worked at Twitter for a while, where I worked on their hate speech systems as well. So I got a lot of experience on that kind of domain, so I have street cred. Cool, so let's dive into it. So before we show the really cool state-of-the-art stuff, let's set a common foundation. So what is NLP and ML for a brief history lesson? So what is machine learning? We're starting from the bare bones scratch. So machine learning is the use of computer systems that are able to learn and adapt, mainly by drawing inference from patterns in data, right? So you have a lot of data. How can we use AI systems to extract those patterns and then model them in a smart way? So let's dive into the building blocks of what a machine learning system is. First things first, you have training data, obviously. You have features you want to model, and then labels for those features. So the objective of what you want to try to predict. You also need a function that maps, basically you have your input features, and it predicts something where you can tune your weights W to change what the prediction is. All right, so you have some function that maps X to Y. That's basically the gist. You also need to have an error function. It's also called a loss function, which tells you how wrong you are, right? So if I try to do a prediction and the real answer is something else, how can we find out how off we are in some way that's numerical? Now, why this is important is this graph right there. And to describe it in a bit more detail, let's say this W here is all the possible combinations of ways that you can make your function that maps X to Y. Right? You can change W in a bunch of different ways, and it changes what your output is. The Y value here is basically how off you are. So if you're really close, you're really far, that's how it computes how far off you are. Now what the loss function does is that, if you know a bit about calculus, is that you can take the derivative, which is the slope, and by taking steps in the slope, you can get closer and closer and closer, and so you get to the best possible solution. So that's what your loss function does. And it lets you do that gradual stepwise towards your final answer. So that's machine learning, and 2 seconds is a whole course on machine learning, but that's machine learning. And yeah, your learn function models stuff in the data. So to dive into a bit more detail, there's two main types of machine learning systems. The first is regression. So what does that mean? Basically, it's how we can have input data, and we can predict a numerical number for that value. So it's a single number prediction, usually. So some more examples, you have, say for example, a bunch of things about a house. So how big the house is, if you're in Toronto, if you have a backyard, if you're nearby a school, features like that, and you can predict what the ultimate house price will be. So a bit more dump bit of details here. Your training data, things like that. Different machine learning functions like these two here. I'll explain one of them, but the rest I'll leave that to you guys to explore in your own time. But different ways where you can map X to Y. For an error function, super simple. All you gotta do is take what the true value is, what you predicted, what's the difference, that's your loss function, easy peasy, you just do the gradient descent off of that. So that's what linear regression is. If you take basic calculus, you should know that this is like a linear line, you have mx plus b, pretty straightforward, where you can adjust m and b to minimize your loss. So that's a lot of words, so I'm a very visual person. So to show what this means in practice, here's an example of just a straight line. I'll hide these guys for now. So right now, we have b is equal to 0, and you have m is equal to 1. So a pretty basic straight line looks like this, right? Now, if I adjust my B, things go down and things go up. That's how we can kind of adjust the line that way, right? And if I adjust M, we can rotate the line like this. So now, let's say, for example, we have a bunch of data points that look like this, right? All of these dots, I don't know if you can really see them in the back there, but all of your dots represents data in your data set. So let's say, for example, like these, like the x-axis is like your input features, and the y-axis is what you're trying to predict. What you can do is kind of tweak this line a little bit to see maybe around there and maybe something like that might be a good estimate of your data points, right? So if you get in some new value, say you have an input feature of, say, 3, you would map it to the red line there, and that would be your output. So that's basic machine learning. You just tweak those parameters until you get your ideal output that minimizes the loss. So that's regression. Pretty straightforward. The other one I'm kind of hand wave is less relevant to us right now is classification, which is how you can predict probabilities for a given input. So let's say you have 5 different categories. You want to predict which category something fits in. So a really classic example is that let's say you have a bunch of animals. You want to predict whether that animal is a cat or a dog. So input features, different characteristics of dogs and cats. Your functions, here's a bunch of them. Here's some loss functions. Again, more for your notes. But the basic idea for something like a linear classifier is similar setup. We have a line that we can say mx plus b. We can rotate, put it up and down. What you want is a line that can separate 2 classes separately. So let's say you get a new input. If your new input is, say, above the line, that's one class. If it's below the line, it's the other class, right? And you can do this with multiple different lines to get multiple kinds of classes. So that's the gist for classification. It's really powerful stuff, but that's kind of the big 2 areas. And so really briefly, just because it's relevant for later stuff, neural networks, really cool stuff. The main gist of how these guys work is that, let's say each one of these dots here is one input feature. So size of your house, if you have a garage or not, if you have X, if you have Y. These are what all these input features here are, right? Each of these lines represents a weight that you're going to multiply this value by to put it in here. So let's say, for example, we have house price. You can multiply it by a learned weight of, say, 0.5, and it would map it to up there. Now, each one of these lines is a different weight, so the output of this guy is the sum of all of the weights multiplied by the values before there. So you get a bunch of these weights and a bunch of these combinations until you get to the very end, you just have, say, 3 outputs, and that's your final prediction. Again, 15 million foot view of what neural networks are. Now we can get to the really cool stuff. So natural language processing. And so natural language processing is a machine learning technique. So inspired by all the stuff we just talked about, we've given the ability to interpret and comprehend human language. So when people talk to each other, how can we use machines to understand what we're actually saying in a way that how humans speak? So for a brief history lesson, the really first way this was done is in a really simple and pretty bad way of doing it, called the bag of words method. So this was invented around 1954. So AI is a really old field, but 1954. And the main gist is that you have a bunch of words. You just kind of count how many of each word shows up, and then that's your input features. So you have the appears once here, doesn't appear anywhere else. You have dog appears a few times, and it's like dog, 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 things like that. And these would be your input features that would describe a sentence. So you feed that into your ML model, and you get some output based off of that. So pretty simple. Pros and cons. Pros. Spam. Some issues. Doesn't do account the order of words, right? So for example, cat eats dog and dog eats food. There's not really an order between like how things are swapped around, right? The other issue is that the vocabulary can quickly explode. Human language is not just the red dog, cat eats food. There's way more words than that. And so the more words you include, the bigger your network gets, and it kind of explodes over time, where it's not really feasible to train. So that's bag of words. Today, we're in transformer models, which are what probably everyone here knows about. Again, I'm kind of skipping way ahead into the future. We're about 2017 now, from 1954. But the main gist, just a skip here, is that it uses this thing called a attention mechanism. Again, there's a lot of math behind this, but all you really need to know is that rather than kind of treating each word as like a number and doesn't care about the order, an attention mechanism learns to kind of map relationships between two words in a sentence. So let's say, for example, you have the phrase, my friend Caleb is really cool, right? You can map the relationship between Caleb and cool. It's probably more relevant than, say, the other words in the sentence. So what transformers learn to do is kind of learn the connections between words together in a much more smart way. The other thing that's really important for us is that the way this works is that the output is that for every word in a sentence, it computes what's called a semantic embedding. So basically, it's a set of numbers that computes the meaning of a word in a sentence, which can be used in later tasks downstream. So let's say, for example, you want to embed that codes the entire sentence, you can use that, but you can use a bunch of different output embeddings for different words. The other thing that's really important about transformer models is the fact that they are pre-trained. So what I mean by this is that basically people like Google and Facebook, they basically look at the entire internet, so billions and billions and billions and billions of documents, and they use what's called self-supervised training, where the idea is that, let's say you have a sentence like this that appears on the internet. You just take one random word in the sentence, you remove it, so you mask it, and the objective is just to predict what that word actually was originally. Now, what's really powerful about this is that if you do this over the entire internet, your ML model learns kind of what the semantics of human language are, right? Because it learns to predict what the next word's going to be over everything, so that you can learn how to learn about language, and you can further fine-tune it downstream on something that's more relevant to you. So it's kind of like having a really good kickstart to what you're trying to do. So that's your blast course on ML. That's about a year's worth of machine learning material and about 4 or 5 slides. So I highly recommend looking at more detail, but hopefully that kind of gives you a good kind of basis of what we're going to talk about next, which is semantic embeddings. That's the meat and potatoes of why we're all here. So as I kind of briefly described earlier, a semantic embedding is basically you have text and you map it to embeddings. Basically, it's a set of numbers. Usually, it's about between 4,000 numbers to about 300 numbers, kind of varies in that kind of range. But it really kind of encodes the meaning of text, right? More on what that means in a second. So let's look at a quick example. So let's say you have this graph here. We have a bunch of different objects. If you were to place the word apple somewhere in this space, where do you think it belongs? Really quick, who thinks B? Put your hands up. Nobody? All right, D? How about C? Right, yeah. So you kind of get the idea where it's kind of like words that are similar to each other are closer in a space. Words that are dissimilar from each other are farther away in the space. So that's kind of the idea there. So that's a pretty simple example. Let's look at one that's a bit more complicated. How about you have these words? So you have puppy, dog, and calf. Where would you put the word cow in this space? What do you think? A. A? That's a really, really good guess. Does anyone else have any other guesses?
C.
Yeah, okay. Both really good guesses, right? So I think they both have kind of validity, right? Because calf is, of course, a younger cow, right? But it's also a baby animal, right? It's much, much younger. When you have dog, which is an older animal, so maybe more similar to an older animal, so maybe want to put it towards B. But the real answer is probably C, as kind of the in-between between both, right? Where you have older animal, also a cow, so maybe we want to put it around here. So it's kind of the idea that these AI models can learn where to put these things in a space. To kind of look at a more advanced thing, let's say here's kind of an output of a traditional model where you have, say, a bunch of greetings, might be up here, a bunch of things around dogs and loving your dog, be around here, and people loving to watch the World Cup, right? So loving things close together, greetings farther away, but still inside of it is close together as well. So those are really, really cool techniques, which is going to power this area we're going to learn today. For a bit of ML background for those curious, This is really similar to regression, where you have an embedding for what is supposed to be there and what is not. You can compute the similarities between the two of them and train that things are close together and not similar things are farther apart. Again, that's machine learning background. Anyway, so that's really cool. So now that we've heard all the background stuff, in this workshop, you will learn how can we build a search engine from scratch over custom documents. So let's say you have a bunch of custom things. How can we search over those things in a really smart and semantic way that goes beyond just keyword search? How can we extract patterns from large amounts of data? Let's say you have millions of documents. How can you actually understand an overall trends in that data? So say customer reviews, things like that. How can you understand that? How can you check intent from the text of users? So if I say, oh my God, I really have to use the bathroom, how can I comprehend it to know, oh, I want directions to go to the bathroom? And also, how can we classify text into different categories using a very minimal amount of data? Using machine learning, you need a ton of data to do any kind of ML training. Using this, you can use a lot of small data and figure out how to classify it together. So, with that out of the way, code time. Woo! All right. So for you guys that don't have the hack pack, you guys all should. There's a link to the notebook we're going to be going over. This is a QR code here if anyone needs it. So maybe I'll take a quick minute. It is going to show up on your phone. I will quickly say, because we're going a little bit fast over the code, I'd recommend maybe looking at the code after the workshop and then just follow along what I'm doing, and then you can look at it on your own time and experiment and tweak things. So maybe I'll wait about 10 seconds, 20 seconds, and I'm gonna go in here. It isn't in the hack pack, and it's probably the first line in the resources, so look at that too. Okay, cool. So that's out of the way. Let's look at some code. Okay, so first things first, I'm gonna run through some basic stuff. This is just all the dependencies. So this will take about 2 seconds just to install everything. Probably should have done this ahead of time, but these are all the things. So this is the first thing you're gonna run into when you run the code. So that's gonna run through this stuff. And then we're gonna go to the meat potatoes. So, like I said, all this code is self-documenting, so hopefully you can use it in your own projects. But here, this is where you're gonna start, where it's this function here. So this is one that you can use in your own projects. It's called the encode function. All it does, I provided 2 different solutions. One of them is using our really cool sponsors, Cohere. They have kind of an API where you can ping and get the exact same semantic embeddings that we just talked about. Maybe I'll also move this slide a bit bigger too, so you guys can read it. And there's also a open source offline solution that you can use as well. So if you have a GPU on your laptop, or you can also use CPU as well, you can use this to kind of encode sentences into embeddings. So let's wait for all this to finish loading here, and then we can get going into some examples. So that's going to take a quick second here. There we go. All right, so let's look at a quick example. So we have 3 sentences here. We have I love cats, I love dogs, and how do I fly to Waterloo to New York? So obviously, I love cats, I love dogs. It's much more similar. So we can encode all of those using our cool ML model that we just got. And if we print off what those embeddings are, once this is done loading, it's usually just slow because we're just starting it for the first time. There we go. So you can kind of see here, it's a lot of numbers, right? So the actual shape of this bad boy is probably about 768 numbers that kind of encode the meaning. Now, how can we actually figure out whether meaning is similar? So one really popular technique is this thing called cosine similarity. So if you've ever taken a linear algebra course, you should know what this is. It's basically just you have 2 vectors, you want to compute the angle between them, right? So things that are really similar will have a really short angle, things that are really dissimilar will have a much larger angle. And this is the formula to do it. I've got a few notes here. But the main gist is that if your similarity is 1, they're exactly the same vector. If they're completely not identical at all, you get 0. And if they're like opposed from each other, you get -1. You usually never ever get -1. So it's usually between 1 and 0, depending on how similar the things are. So let's look at this in practice. This is just a function that does that cosine similarity for you. Now we can see here, for I love cats, Obviously, it's identical to I love cats, really similar to I love dogs, and completely separate from How Do I Fly from Waterloo to New York. So that's a basic example there. Now let's look at some actual practical applications of this stuff. So I have a quick data set here that I've prepared for you guys. All it really is a bunch of movies. So I'm a big movie guy, love movies. So it's just a data set of about, I think it's like 36,000 movies. And all it has is basically the title of the movie, the year it was published, the genre, language, director, actors, and also the description of the movie itself. So really quick, before we kind of dive into the next thing, what do you guys think in text would describe what a movie is using these categories? Someone have any ideas?
Description.
Yeah, description's pretty good. What do you think?
Duration.
Duration's pretty good. Yeah. What else? Do we have any ideas?
Genre.
Yeah, the genre. Yeah, awesome. Yeah, those are all really good ideas, right? So ways we can kind of encode in text what something means. For the sake of demo, I've already pre-picked about 5 of them. But again, you guys can play with this on your own time and kind of see which ones work best for you. So for this, we have the title, the description, the date that it was published. So some movies that are published around the same time period might be more relevant to each other. The genre, the actors, and also the director of the movie. So what this function here does, just takes all of those, maps them together, and so we get a really nice kind of description in text of what a movie is. So that's step 1, right? We want to figure out how can we represent what we want to search in text. So we have all that there, and next we can encode everything. So I'm going to click this, and I'm going to quickly cancel it, just because it takes about 5 minutes or so to run this. So for the sake of time, I'm going to skip it and just download the result. But you can use something like the Cohere stuff, which works a lot faster. Or if you have a more powerful GPU, you can also speed through this. I have a 4090 at home, and it runs through this in like about 20 seconds. So you can change it accordingly. So I'm just going to download the results here, which is just the exact same output of what this originally was, but run on my really cool GPU at home. So the result here, we have our 35,000 movies, and then all the numbers that represent what that movie is. So how can we use this stuff in practice? So here's basically a library. I'm going to show you guys how it works. It's this thing called Facebook AI Similarity Search. All this really does is that the cosine similarity thing we showed earlier, it just does this really, really fast in C++, and you can use it in production. We use this all the time at Twitter. It's kind of how you can kind of do similarity things really, really fast. So click this, it'll just build the index. So take about a few seconds. Again, from my experience, it's usually pretty fast, but worst comes to worst, we can just download a pre-made one as well. So, seconds. I guess really quick, I'll pause. Is anyone here super lost about anything? No? Cool. Okay. I am going to be here all day mentoring, so you guys can feel free to come up to me if you have any questions about any of this stuff as well. So this will take a second. Might abort in 2 seconds. Download the pre-made one. Usually it's pretty quick. So yeah, I give up. Let's just download the pre-made one. So we can do this. And again, it's just the result of the index. And to show what this means in practice is that, let's say, for example, we have the movie Star Wars, right? It's one of my favorite movies of all time. Star Wars Episode 6, Return of the Jedi. So we have our description of the movie, the genre, all the actors, things like that. So what do you guys think should be the output of this if you want most similar movies out of this? Any guesses? Yeah.
Other Star Wars movies?
Yeah, exactly, right? So let's see if that actually works. Fingers crossed. So we get the movie. We can see all of the indexes that it looks for, and then print the result. And yeah, we're correct. So we can see all the different Star Wars movies, because that's what's semantically similar to the description of the Star Wars movie before, right? And so you can see all the descriptions. For example, we have Star Wars Episode 6. The most similar to that is the one that came right before it, right? And you also get all the other Star Wars movies as well. So that's really cool. And again, just for functional reasons, you can tune this to see how many things you want to retrieve. So just the top 10 or the top 5, you can change that accordingly. So that's really neat. Let's look at one more example. This is a movie here, which is the Princess Bride. So you can kind of see a quick example here. It's a young boy's grandfather reads him a story of a farm boy turned pirate who encounters numerous obstacles, enemies, and allies in his quest to be reunited with his true love. Sounds like an awesome movie. So if you take that and then do a similarity search, what's interesting is that The Princess Bride doesn't really have any sequels, right? It's just a random movie we know nothing about. There's a new one or a second one. The movies are similar to The Princess Bride. So if you look at the output, we can see a bunch of movies that are all kind of fantastical movies about pirates and Beauty and the Beast and other ones that are kind of similar movies. One that I thought the most interesting from this result was the movie Nemo, which is not Finding Nemo, it's a different one that came out in 1984. So I don't know if anyone here has ever heard of this movie before. I certainly haven't. But when I look at the description of the movie, you can see it's actually really similar to The Princess Bride, right? And so right now, we have basically a search engine that you want to recommend similar movies to users. You can search using this and get similar movies that way. So that's really cool. But so before we use kind of movie descriptions, can we just use random queries about how someone would actually talk to an ML model? So here's an example of horror movies with animals. That's not a movie description, doesn't fit our prior setup for movie descriptions. So if we encode this description, we encode it, get the search, we can see all these movies are all horror movies talking about animals. So creature feature, animals, and live animals, and they're all horror movies featuring animals. So really powerful technique. Again, one more example is comedy movies featuring weddings, right? If we encode that, we can see we got Wedding Crashers and Happy Ever Afters and One Small Hitch. And it's all movies about weddings. Again, this is an example of movies. You can do all kinds of different stuff with this in different kind of sets of documents. One really cool example, this is basically one of my work at Twitter, was that let's say you have a sentence that looks like this. So Bert and Ernie are two Muppets who appear together in numerous skits on a popular television show, United States Sesame Street. What you can do is take the embedding of, say, the words Bert, Ernie, Muppets, United States Sesame Street, so different kind of named things. Then you can make embeddings of basically the entirety of Wikipedia. So you have all these descriptions of Wikipedia articles, and then search off of that, and you can kind of find out what these things actually mean. So for example, Bert is not referring to the ML model Bert, but referring to Bert from Sesame Street. And you can get the description of what Bert is, and different kinds of things like that. Another good example is like talking about the Beatles. So if you had, John, Paul, George, and Ringo are my favorite musicians. How do you find out who John, Paul, George, and Ringo are? You can actually figure out what that is, and not just some random dude named John. That's really cool. Again, exact same techniques, just doing the search for embeddings. So that's one really cool application. Let's look at some other ones. So as I kind of mentioned earlier, embeddings are massive. It's like 768 numbers, right? So we can't really get that really cool example we had earlier in our slides, where it was like a 2D thing. You kind of see where things are. We can't really make sense of this data, right? Because it's so big, we can't plot it. So what we can do is this technique called dimensionality reduction. All that really means is kind of figuring out, is there a way that we can map all these numbers into a 2D space without losing any of its information while doing that? So to quickly show what that looks like, we'll take the first 3,000 movies. We'll get this example here. I'll just preload this in the meantime. But this is a really cool tool called TensorBoard Projector. But I'll show you guys what it looks like once it loads. Give it a second. Really quick, any questions so far on anything? Cool. Okay, so this right here is a 3D space that represents all of the embeddings of the first 3,000 movies. What we did is a technique called PCA, which is Principal Component Analysis. All it really does is that it says, out of all the numbers, pick the 3 that kind of separate the data most in a way that makes most sense. So you kind of see here, it's a little bit abstract. It's not the best technique, but it's really fast. Another really cool technique, this thing called TSNE, or TSNE, which is invented here in Canada, by the way, which is really cool. But it looks like this. So this is a really cool animation, but what we can see here is that it's using machine learning to try to figure out how to map the space in a way that says embeddings that are similar to each other are grouped together in a space. So let's say we want to mouse over here. We might see a bunch of movies about young reporters. Let's see over here. Maybe I'll reduce this down to 1 and stop. But you can see if I focus on this embedding here, it's all about reporters doing stuff. And Blondie, I guess, is a bunch of movies from the olden days. Things like that. Also used in a 2D space as well. And you can kind of use this to extract patterns in your data. So let's say you're looking at a bunch of reviews, and there's a big cluster of everyone talking about the same thing, and it's all one big clump of data. You can use something like this to figure out what the actual patterns in your data are. So let's dive into a bit more on some specifics here. Here's another technique called UMap. It's my favorite. Again, it does the exact same thing. Just kind of figures out, for all your data, how can we map it in a 3D space in a way that doesn't lose any meaning. So we do this, map it a few times, plot on a graph, and you get something like this. And again, this is pretty good. We could probably do better. But you kind of still get an idea of a bunch of Western movies that are over here and things like that. So let's actually look at a bit more information here. So let's say we have the genre, right? Does the genre actually show up in this space in a way that makes sense? So here's a bunch of genres for all the movies. We can take basically the first one, all this does, so history, drama, comedy, horror, things like that. We can plot the exact same thing again. Again, I'm just going to skip ahead and run all of these in parallel. So once this is done loading, and projector. There's a little parameter here, color by, so we can see what the colors actually are. Give it a second here. Boom. So color by genre, you can see all the colors in the genre space. You kind of see the PCA doesn't do really that good of a job at this. But if you go over to something like UMap, which I think I have a much better example below. But once that loads, boom. So we can see all our movies in the space, kind of all over the place, but you should kind of see a bunch of orange points in one spot, a bunch of blue and green points in the spot. All these represent different genres in your data set. Now, what's really cool is that we're kind of using this as kind of an after step, right? So we have all of our embeddings in the space, and then we plot genre after the fact. But can we actually use genre as kind of an informative feature to say, hey, maybe we should group things of the same genre together, but still look at the actual semantic meaning as well. So we can kind of hint these models to kind of make things a bit more using kind of real-world knowledge. So this step does. So all this stuff is doing is mapping the genres to just numbers instead of words. But we can use this and call it target weight. It kind of says, look at the actual meaning of the text, but also have a small weight and kind of say, maybe you should also look at the genre as well, with a weight of 0.2 with a max of 1. So we do this, map it all out, plot it, and we get something that looks like this, which makes a whole lot more sense. We have a bunch of thriller movies all in one corner, and a bunch of movies that are similar to each other, things all around horror movies, thrillers are close to each other, right? Because they're kind of similar. Whereas things like, romance movies are the polar opposite of, say, thriller movies, right? And you kind of get that similarity in the space here with the meaning as well. So that's really cool. For a bit of background for everyone as well, these are all JS objects. So if you want to embed this into your actual work, say your website, it's really easy to kind of just plug this out and put it into your apps as well. It's all using Plotly. It's a really cool library. So that's really cool. Now, one other technique we can do to kind of color points is this thing called K-means. So to really high-level describe what that is, so let's say you have a bunch of points that look like this. It's going to restart the animation in a second. But the idea is that let's say you don't know anything about the data points and you want to figure out what the actual groupings are without knowing anything else. So what you can do is that you can kind of set, let's say for example, in this case, 3 points, so 3 spaces. And the idea is that the model learns to kind of slowly nudge these points until the average distance between all the other points is minimized, right? So it keeps kind of nudging and nudging and nudging until it kind of optimizes that the space is small as possible. So this is really cool if you know anything on the data, and you can get kind of pre-computed groupings using that. So to show what that means in practice, let's say in our movies there's 10 genres. We can do this, run, run, run. I'll skip over the tensor board for now, just because it takes a bit of time to load. But if we plot the results, it's a little bit worse, right? But you can kind of get an idea of things that should be similar to kind of a grouping of space are kind of highlighted for you. So this is really good. Let's say you have a lot of data. You want to figure out, you have a lot of reviews about negative things. This could kind of find that for you in a kind of a pattern of data. Now, the other thing you do too is that let's say you have these groupings. How can we actually understand what those groupings actually mean? That's where you get something that's basically this function here, something called TF-IDF, but to kind of high level describe what this is that it kind of just figures out ways to count words and finds the most prominent words in a given paragraph. It kind of cuts things like the word like the and things that don't actually mean anything. It looks at more words that mean a lot of sense. So to show what that means, here's all the different groupings that the model before found. And we can see that for one of the clusters is all about young love and woman, man, life, new girl. So you can kind of guess, probably talk about romantic movies, right? Another one is, town, man, young, gang, war, West sheriff. So that's probably about like Western movies, right? Or you get one talking about like murder mysteries, murder, man, woman, young, police, wife, detective, right? Another one could be things like World War II, I think is one of them. Yeah, war world, American story, British, young, army, things like that, right? So you can use this at a high level, because right now, like I said, we have 3,000 movies, right, with this current setup. Actually, no, it's not true. This is 36,000 movies, right? It would take forever to look at all those movies and figure out what the patterns are. But using this, we did it in like 2 seconds, right? Because we use AI to extract those patterns really quickly. So that's cool. So that's one example of kind of understand overall kind of macro patterns. Let's look at some other applications. So one is content understanding and classification. This is a really, really big topic, but it's kind of the idea of how can we use these large language models, so we can understand human language, to kind of classify text for us. So here's an example. Here's a bunch of questions about Hack the North, right? Thank you, GPT, for doing this for me. But basically, here's a bunch of examples. We have questions about the history of Hack the North, or what's the location of Hack the North, and things like that. These are all questions that we already know ahead of time. So let's say their users have been asking questions, things like that. And they can tell you, actually, I was looking for general info, right? So this is your data set questions and the answer of what they're looking for. What we can do is, again, using our ML models, we can instead, oh, I didn't click this answer first. There we go. What you can do is that rather than encoding the answers, which are all of these things here, we can encode the questions, right? So let's say here are a bunch of questions, and we can say if a user asks a similar question semantically, something that we already know, give them the answer that the other person looked for, right? Because they probably want the same thing. So you can build our index. So similar to before, to search things, again, much quicker because it's only about a few things. We can say, here's a question, where do I get food? Right? That's a normal question. Again, this question, you can kind of take my word for it, but there's nothing else here that talks about food and where to get it. So if we click this in search, we can see that out of the top 5 things, the top 5, 3 of those most relevant ones talk about directions, right? So we can continue that, say, all right, they asked about where to get food. Here's the answer, where can you give a more better answer than just this, but looking for locations and directions. You can change this to be something else. Like, let me think of another category we got here. Let's say, how do I sign up? So let's say here, how do I sign up? And you can search, do this, and you can see the top 3 about registration questions. So you can use that. Now, this is also going to be kind of a feedback loop where you can give this answer and say, hey, was this relevant to your question? Just how basically all company chatbots work. You can say, and if they say yes, you can add it to your database, and now you have a more accurate representation of questions. The other thing I'll quickly mention too is that this can be used with something like ChatGPT, where you can retrieve a bunch of documents based off of their intent, and then add that as a prompt to ChatGPT, and kind of have your own custom information in there too. So that's really cool. Again, talking about registration. We can look at one bit more complicated example. So this is one talking about airlines. So we can print this here, and we can see a bunch of questions about airlines. So things talking about flight details, how expensive a flight is, what airlines fly different places. So this is a much more complicated data set because it's a lot bigger. So what we can do is that instead of doing this kind of similarity search, we can train a really small machine learning model to interpret embeddings and then predict a class using these embeddings. So similar to before, we can encode all of the text, which is again all of the questions. We encode that, and then this is just code that trains the linear classifier that I showed earlier, which again just points to two classes, a line that separates the two classes. Again, exact same technique we talked about before. So we can say, look at the first 4,000 things, we can test it, the last 4,000, or last things like 400, to see how well we did. So that's all this code does, is that it fits it. We have our new ML model. We can see the accuracy is about 99.59%. It's pretty good. And then, so to catch an example, here's a test set. So the real answer is this. This is a query. That's what we predicted, which is pretty good. To show an example in practice, we have how much is a flight to Waterloo? We can see that it directly predicts airfare. So rather than having the noise of being like, oh, there's like 3 things that talk about airfare and 1 or 2 things about something else, this will just tell you airfare, right? So it's much more direct and can kind of work better if you have the time to train an ML model. So it's about airfare. Another one can be, what flights fly to Waterloo? And then we can see we're asking about flights. So that's kind of another technique here. We can actually directly predict what categories things put into. So that's pretty much what I've got. I've got a ton of stuff here. Thank you so much for listening. I know it was a lot of information. Again, I'm going to be here all day. So if you have any questions, feel free to ask. Or if you have any questions now, I'd love to hear it. There's one extra slide here for the scavenger hunt, I think. So if you want to scan and answer that question, that'd be pretty quick. Yeah, I'll pause here. Yeah, does anyone have any questions?